Thank you very much. Actually, it's a pleasure to be here. It's my first time in Cape Town, actually in South Africa, and even furthermore, in Africa. So it's a big first in several instances. So it's my pleasure to introduce you to cosmology in a way which might be slightly different from what you've received before. So I'm going to give you first an overall picture, and then we'll focus particularly in a few instances where we're now investigating. We're now trying to understand what goes on in those features. So it seems that what you've heard probably in the basic courses of GR and cosmology is that things occur nearby. We measure them with whatever we've got, CMB, the logical structure, and then we try to infer what goes on in the early universe. I'm going to make a one-to-one mapping between what happens before the end of inflation and what happened after the end of inflation. You'll see that there's a connection between those two, and the typical image that we have in cosmology that we started at some instant and we're measuring here, 13.7, 13.8 billion years after, is actually a distorted image because it is describing the evolution of the universe in a time variable, which is the one that us humans use, cosmological time. Okay? The actual time, in GR, you can redefine all coordinates, and the actual time that in cosmology we should be dealing with is not cosmological time, it's not even conformal time. It's a scale factor. It's simply the size of the universe. That's your clock. Okay? So, in terms of the size of the universe, the actual... Can we break this? Yeah. I know I have.
Maybe once you've done the lights as well, but on the wall.
The only thing I need is half board. Go slower. Maybe fast.
Up.
There's no need to turn off the projector. That's okay. Thank you. Right, so this is the universe timeline in log of A, which is the number of epochs. We observe things here. This is now. Whatever happens here actually, on the very large scales, was within the horizon during inflation here. Say 65 epochs before the end of inflation. So I'm going to make a mapping between what goes on in this period with what happens that you're familiar with, and some things you might not be familiar with, in this period here. So the pre-Big Bang, Big Bang occurred at the end of inflation, with the post-Big Bang. Okay? Now all things that we're familiar with, like the CMB, logical structure, the formation of galaxies, and so on, lambda domination, recent period where some new agent is driving the expansion of the universe, occurs very close to today in this log of the scale factor. And I'm dilating, making the dilatation of this frame in some cases just to show you what happens. Big Bang nucleosynthesis, in the end, would have happened there. Most of the epochs of evolution of the universe are unknown to us. Okay? We can only get information from a few of these phenomena by measuring things. Getting, for instance, the light element abundances and know about the baryon content at nucleosynthesis, or measuring the distribution of galaxies in our universe from light that reaches us from redshift 2 or so, and trying to guess from there what is the content of the universe in dark matter and dark energy. But those things occur just in the last few epochs of our universe. Surprisingly, and this is the thing which we've learned in the last 30 years, is that whatever happens now actually has a connection to what happened in the early universe. In fact, things that happen here translate to things that happen here. and so on. This one-to-one mapping, you will see, will allow us to, from measuring things today, guess or deduce, infer what happened in the early universe. So the physics that we know works in the lab, and we are very familiar with, electromagnetism, even gravitational collapse, nuclear forces, all of those have their mapping onto phenomena that occur during inflation. And this is what I'm going to concentrate in these lectures. I think it's the original way of describing our universe. We will see, among other things, at the end of the lectures, lecture 4, on Friday, we will see that some of the phenomena that occurred recently, like the formation of structure, the nature of dark matter, actually may have to do with phenomena that are occurring, say, 20 epochs before the end of inflation. The formation of primordial black holes, peaks in the power spectrum. So things that were thought to be completely disconnected, I'll show you in these lectures, might have a common origin. And this common origin could be accessed through observations today. If it were for this one-to-one mapping, I'll show you why we don't have such a mapping in this lecture, we would not be able to infer these connections that for us nowadays just simply look like coincidences. Okay? Very good. So let me go on with the lecture. I'll show you now how some of the phenomena can be turned lights off. Where is it? This one? Yeah, very good. So the outline of this first lecture will be first to get you familiar with some of the shortcomings of the Big Bang and how does that tell us that we need to assume that in the early universe we had a new period of expansion of the universe that we call inflation. And we'll see how inflation, which will be at the base of this one-to-one correspondence, is very rich in phenomena. We thought it was just simply a tremendous expansion of the universe. That's not true. It's much more complicated than anything that you probably have heard of. Okay, so what are the shortcomings of the Big Bang? First, you know that the space-time structure of the observable universe has very peculiar properties. Why is the universe so close to spatial flatness? That's something which in the 70s became a puzzle. It was the first time that people had observed the distribution of galaxies and they said, wow, this universe seems to be extremely flat for what I would have expected. And I'll show you why it is unusual in Friedmann or working universes. So perhaps we need some other mechanism, something to tell us about the early universe, which is modifying our initial conditions. Another of those basic questions was, why is matter so homogeneously distributed on very large scales? So it's true that locally, and now we know pretty well what is the distribution of mass, that is, galaxies around us, we have been able to map, and this was not true in the 70s, we have been able to map with exquisite precision our neighborhood. From here to 80 megaparsecs, we know that we just are part of a huge superstructure called the Laniakea supercluster. This Laniakea has hundreds of thousands of galaxies, and those galaxies are not static, they're moving. And they're moving in avenues, so there are flows of galaxies within the universe. We're just simply moving along one of those flows towards the famous Great Attractor. But very close to us, it's really like surfing, we're surfing on a flow. Very close to us, there's a huge void which separates us from dense species, another supercluster. Okay? So the structure of the universe is not homogeneous at all on small scales. There are plenty of voids, places where there are almost no galaxies. And there are huge concentrations we call superstructures, like superclusters, okay, and clusters, as well as these cosmic wave motions of galaxies along these avenues. So, however, if we look even further away, not just 80 megaparsecs, 100 megaparsecs, 1 gigaparsec, well, now we're reaching decades of gigaparsecs, then the universe, on the whole, statistically, looks essentially homogeneous. What does homogeneity say? That means that it's a mathematical statement if we move ourselves to a different point in space and we observe that universe to be essentially identical to this other one, that means that it is invariant under translations. That's nothing but homogeneity. The universe is essentially statistically. I insist on the word statistically. It's not true. Specifically, if we look at the particular concentrations, they're going to be different from one place to the other. But on a statistical sense, on very large scales, this is perfectly homogeneous. Another property of our space is that if we look around us at any direction, we again observe the universe to be essentially identical. That is, it's isotropic. Okay? Mathematical theorem tells me that if we're not special in any sense, and any observer in the universe looks around and sees the universe to be isotropic, then necessarily the universe must be homogeneous. Yes?
What is the scale of homogeneity?
Excuse me?
The scale of
homogeneity? Okay, we measure this with the local survey like the 2-mass ASE, Consensus catalog in Redshift, and this is something like 100 megaparsecs. Okay? Clearly, below 100 megaparsecs, we've measured the distribution of galaxies in the Laniakea. The universe is not homogeneous. Okay? So beyond 100 megaparsecs, you can coarse grain, average out the distribution of galaxies, and it does look homogeneous to very good accuracy, at least to 1% accuracy. We should state homogeneity. That's something which we realized with Bellido also. We have to state homogeneity in a statistical sense and under, as usual in physics, certain confidence level. And here is 1%. Okay? 99% confidence level, the universe is homogeneous on 100 megaparsecs. That's the precise statement. Okay? Now, not only do we have the difficulties of the homogeneity and flatness of the universe, that is, the background space-time, how do we describe the measure, but also there are difficulties with the perturbations of this measure. In particular, we might ask, how did the thermodynamic spectrum of density perturbations, what will eventually become galaxies and these flows, this huge cosmic wave of structure, where did it come from? How did we ended up having fluctuations which had a given amplitude and grew through gravitational collapse to become what we observe? In a perfectly flat and homogeneous universe, that would never have happened. Okay? That was the difficulty with Newton, trying to understand structure formation. Moreover, something that we still do not understand, we're trying to find reasons. I will give you at least one possibility in the third lecture from preheating, is where does all the energy of the universe come from? Okay? So we see plenty of galaxies out there. We see that we are at every cubic centimeter there are 400 photons from their universe which have been redshifted to the microwaves, and that's a lot. Where do those photons come from? How did the universe create matter and energy? Moreover, it's not just enough to produce matter and energy. If we want to be here in a collapse system that is mostly contains matter and, among other things, baryons, we have to make sure that the antibaryons, which we know through particle physics were there in their universe, must have gone away. Either we've been able to segregate baryons from antibaryons, something which is extremely difficult, or somehow there was a tiny overproduction of baryons, what we call baryons, but really antibaryons, over the other one, so that eventually when those baryons and antibaryons are annihilated and produce the photons, we're left with a residual component, which is ours, ourselves. We're made of baryons. The origin of these matter-antimatter symmetry is still a mystery. We know from fundamental physics, particle physics, that that mystery requires certain laws, certain conditions, it's called Scalar conditions, and we will deal with those in the third lecture. How did we end up with the baryon-dominated universe out of something which, as we will see during inflation, was perfectly baryon symmetric. Okay. And something which is much more fundamental and perhaps much more difficult to address, and some of you here work on it within the context of quantum gravity, is how did the universe have a beginning? Where did it all come from? Are we just a quantum fluctuation out of nothing? Is it possible that somehow the same laws that applies to particles popping out of the vacuum, as long as you submit enough energy which can produce particles which then eventually expand? Could this happen also for space-time? Is space-time also a quantum phenomenon that can pop out of the vacuum? That's a fundamental question. perhaps is behind the whole structure that I will describe here, but unfortunately I will not have enough time to go over, and it's related to these dots here. Perhaps the universe, much before the scales that re-enter back in the horizon today, had a structure, a very large scale structure, much bigger than anything within our observable universe, which can account for these first beginnings, the actual true origin of the universe. We don't know. We're still under investigation. It comes under the words of stochastic inflation in the context of fundamental theories of particle physics, like string theory. You have to assume certain properties of your initial vacuum, and these might give you a whole landscape of possibilities. That's still under research. Okay? Most of what I'm going to describe to you in these lectures is what I understood. These is still under investigation. Okay? So one of the questions that rises out of that scenario is, what is the global structure of the universe? And this is important to realize. It's true that the scales that we've been able to approach as human beings, which is just people, animals that only stand up like a meter above the ground on an ordinary planet, on an ordinary star, in a forgotten galaxy in the universe. It's amazing that as animals that can think, we've been able to comprehend what happens around us all the way to 13.7 billion light years away. But that's not all. We are aware that this observable universe, the one from which we get light, is not all that there is. It's perfectly possible that we're just a simple bubble, right, at a distance much far away than the observable universe from a completely different structure that I call the global structure of the universe. We happen to live in a little island which has gone through a particular evolution, and it might be that at distances hundreds or millions or trillions of times the observable universe, the properties, the physical properties are very, very, very different. This global structure of the universe, again, it's speculation. We do not have any evidence that there is such a structure on very large scales. But the theory, in particular inflationary theory, predicts that there should be such a global structure. It's called the stochastic inflation formalism. Some of the lectures, the notes for the lectures that I have described, I have given to you, touch on this very global structure, but I will not. I don't have enough time to go over this. Okay? So I'm just opening windows for you to explore. If you want, we can discuss them afterwards, after the lectures. Okay, so these are the shortcomings of the hot Big Bang. Let's see one by one how do we arrive there. The Einstein-Friedmann equations you're very familiar with, I guess, through some basic cosmology course. They relate the rate of expansion of the universe, first derivative of the scale factor, what I have used here as time variable, with the matter content and the curvature of the universe. On the other hand, this is, as I described in the lecture notes, this is nothing but a constraint equation. This is due to the reparameterization variance of the equations of Einstein. The actual evolution equation is this one. It's second Friedmann equation. It tells you how does the universe accelerate, as usual in any evolution equation, second order differential equation. You give some initial conditions set up by Hamiltonian constraint, and there you can ask from the matter content what is the acceleration of the universe. You see something very peculiar. With ordinary matter, with positive pressure and density, the universe should be decelerating. So this is something that Lemaitre immediately found out when he solved the equations, after Friedmann had written them down. He realized, wait a minute, if I fill my universe with any kind of matter, the universe is going to expand, and it's going to expand in a way which is decelerating, which is natural. If you fill a box of matter, and you see like gas, and you let it expand, it's clear that there will be gravitational interactions among particles of this gas. And this will attract each other, and will make whatever expansion is nowhere. It will decelerate the expansion. What has surprised us in the last decade and a half is that this term seems to be, today, negative. So somehow we must have conspired to have some negative pressure, since negative density we don't know how to deal with, so that this term is negative and the universe is accelerating. This is a mystery. And we will deal with that in the second and the third lecture. Okay? So not only do we have the Friedmann-Einstein equations, we also have an energy density conservation. We know this is nothing but, again, the invariance of the action under rebalanizations, which tells you that some current should be conserved. It's a method current of the rebalance invariance of the theory. It will happen for any covariant theory of gravity, even if it has scalars. So in our case with GR, which I'm going to concentrate on exclusively, the conservation of energy momentum tensor gives you, in the case of a Friedmann-Rosen-Walker universe, with homogeneity and isotropy, so described as a fluid with just density and pressure, gives you this relation. The variation in time, cosmic time, must be related to the matter contained this way, roughly. So the only thing we have to add to these equations, it's things that will connect pressure and density. In ordinary fluids, we know that that's called the equation of state. The equation of state is an extra ingredient we have to add up to our equations with the final behavior of the fluids. Once we characterize our fluid, for instance, this way, barotropic fluid would have pressure and density linear to each other with a constant, or it could be a varying quantity in W. Then, once we know this connection, this equation of state, automatically we know what is the rate of expansion of the universe at any time. Okay. Let's rewrite those evolution equations in different variables. First, I will describe our density parameters. It's the energy density, for instance, for matter, with respect to the critical density. The critical density in terms of the rate of expansion is this quantity. In general, it will depend on the time at which we are. Okay, it's not a constant. Today, omega n, today would be this quantity. When a is 1, we would have omega matter. And that's the quantity that we can measure. Nowadays, with the CMB and logical structure, we can measure with to the few percent precision, which is extraordinary. 20 years ago or 30 years ago, that was completely impossible. We could never reach such an order of precision. That doesn't mean that we understand all the contents of matter. We know at least baryons. We don't know the nature of dark matter. And we will deal with that in the last lecture. Another component today, it's worth exploring. This is what we call vacuum energy. In principle, that quantity that I have written there, the cosmological constant, may not be necessarily constant. It could be some vacuum energy which is changing as a function of time. And nowadays there's a whole area of research trying to understand whether this quantity is constant, whether it's varying in time, how are we going to measure the variations in time, both observationally and with theoretical models that will describe such a variation. Moreover, it might be that GR is not the whole description of the expansion of the universe today on very large scales. We might have to modify gravity, and we will hear about that from Jose this afternoon, who will give these lectures on modified gravity. Now, let me reduce my ambition and concentrate here mostly on a cosmological constant. Okay, so for us, dark energy will be constant. It's energy density which is constant, which we characterize by nothing but the cosmological constant of Einstein. In this case, this variable y, omega of lambda, as a function of the scale factor, has this form. Great. Then the only thing we need to know is how does the parameter or the variable x and y evolve together. It's interesting because this is nothing but a nonlinear but homogeneous system of equations. Okay, so you can write this, the differential equation that each of these two variables satisfy, and you have this simple equation where the time variable again is log a. Okay, it's n, the number of evolves today or in the past, doesn't matter. Now it's very simple in this nonlinear homogeneous system of equations to find the critical points. Okay, it's obvious x equals 0, y equals 0 satisfies the x prime and y prime equals 0, but there's also x1 and y0. X1, y0, y0, and x0 and y. Okay? That means that we can draw the phase diagram in the plane of x, y, and see where the critical points are. So 0, 0, 1, 0, 0, 1. Okay? And draw here the different like, so if we started close to, say, this region, and we let it evolve, it would move along this trajectory. And as a function of time, or scale factor, eventually we will reach omega lambda equals 1. So omega lambda equals 1 is an attractor of the evolution. Omega m equals 1 is a repulsor. So there are, in phase space, attractors. And these attractors are going to determine the properties of the space-time. We're going to see that whatever our initial conditions, if we let the system evolve, it will go into a certain direction. So if we find ourselves in a particular region, say where omega matter plus omega lambda is 1, we might immediately ask ourselves, how come are we here? Is this natural from the point of view of arbitrary initial conditions? What makes us special? Why should we observe our universe to be essentially flat? As you will see, this is the line corresponding to flat universes. And why are we right here, as we will see in a minute? Why does this observation suggest that we're at a particular point in this phase out? We'll see that this is what brings out the shortcomings of the Big Bang theory and open up the understanding or the inclusion of inflation within the whole paradigm of the evolution of the universe. So, in particular, if we explore in detail one of the most acute difficulties of the hot Big Bang theory, that is the flatness problem, we can ask, this is the Friedmann equation, we can write the omega density parameter this way, a new variable, let's not confuse it with the x that we had before, omega m of a. But we did I share? Then we can write this x, remember it's something like a constant over rho a squared. Rho is the density, it evolves as a function of the scale factor, so we have 1 over the scale factor squared times rho. Using the evolution equation from the conservation of energy momentum tensor in an expanding universe, we arrive at the equation of motion for this variable x, which tells us that variation with the scale factor should go like a constant times itself. That's quite interesting because x equals 0 here would be unstable if you have matter and radiation, that is for most of 3w positive, that is you make a small perturbation with respect to 0 for x, this would very quickly grow. Okay? If x is positive or negative, whatever its sign, and remember, positive or negative would mean that you have a closed universe or an open universe, we will very soon, 1 over, sorry, as the scale factor squared during matter and during radiation, sorry, and as the scale factor during matter. So in a few e-folds, this grows very fast and you are away from the good point. So how come are we so close to the universe which is flat? So to parameterize this in a much more specific way, let me convert that evolution into a series of intervals in time. Imagine that we started with a variable x, the deviation from 1 for omega, and some initial time, x in. Then assume somehow this universe becomes radiation dominated. If it becomes radiation domination, the density decreases like 1 over the scale factor to the 4th. It's expanding, so it's diluting, but also the energy is diluting. And this 1 over the scale factor to the 4th means that x is going to grow like the scale factor squared. A and t are proportional, inversely proportional to each other, and therefore this means that the next period of radiation domination should have a factor of the initial temperature over the final temperature of this epoch. Radiation epoch ends when matter starts to dominate, that is radiation matter equality. I have parameterized by T equality, to the factor 2 from this square. And then you have, after matter radiation equality, you have the growth due to the matter domination. This is a factor 1 plus C. I will ignore for the moment, it just will give an order 1 correction, the evolution of the universe since lambda domination. That's only going to give you, since it hasn't gone more than 1 e-fold, the factor 1. Correction. Now, the variation of omega with respect to 1 from the CMB is measured to be 1 part in 10 to the 3. We're very, very close to flatness. So, in order to arrange this to be 10 to minus 3, it's needed, the furthest that we know inflation has, the evolution of the universe has gone through is through Big Bang nucleosynthesis. We know when the universe was about 1 second old, all the light elements were cooked, mostly the helium that we cannot produce enough through stellar evolution to account for what we observe, 25% in mass of the universe. That necessarily means that the universe must have gone through radiation domination and Big Bang synthesis, and therefore we can take at least for granted that at the time of Big Bang synthesis, when the temperature of the universe was about an MeV, the universe must have been through radiation. So what is the coefficient that I have to put in order to observe x naught to be less than 10 to the minus 3 today? Surprisingly, if you substitute here 1 MeV, this is a temperature equality about an EV, we add here, multiply by the factor 10 to the 3 or so for the evolution during matter domination, we end up with a condition that the deviation from 1 at Big Bang doesn't have to be not bigger than 1 part 10 to the 18. That's a tremendous fine-tuning. That means that the universe today might look essentially flat to 1 part 10 to the 3. That's okay, you could account for that. But if it's 10 to the minus 3 today, and we know perfectly well the matter content all the way to Big Bang nucleosynthesis, that means that at nucleosynthesis, it could not have deviated more than 1 part 10 to the 18. Now, if we go much further, and of course we don't have any measurement today that allows us to really go far into, say, the scale of energies that we can probe in particle physics, the TeV and the LHC. But if we extrapolate those energy scales all the way back, we might end up with numbers like 10 to the minus 50 or so. So that is really a tremendous frontier. We better have some dynamics next time. Okay, moreover, not only do we have the difficulty of explaining how did the universe become so flat today, since it was unstable, and any tiny deviation would be much bigger than 10 to the minus 3 today, there's something which is much more fundamental. And that is something we're familiar with the moment we understand that space-time is dynamical. There are horizons, so things that happen at a distance bigger than a given one, which is we would call a horizon, it's just simply inaccessible to us. We cannot see what happens beyond a certain distance. Simply because in order to see what happens, we have to receive information from it. Something, light, gravitational waves, whatever, neutrinos, must have traveled all the way to from that distance to us. Now, if the universe has a given h, which is not bigger than a certain quantity, then there is an actual horizon. It's called the cosmic horizon. We cannot know anything about the universe at a given distance bigger than such a horizon. Now, those horizons, if you look at them, and I have drawn the past icon from us, from any point in our spatial hypersurface, backwards in time, and I beg your pardon, but I have used straight lines. We know that those curves are not straight because the universe is actually expanding. There is time curvature. We've agreed that there is no spatial curvature, but that's, I mean, we're talking about space-time here, and the universe is expanding, and therefore there is curvature in time. This curvature in time will actually convert those straight lines into curved lines. Okay? The actual horizon is 3 times during the matter era, as you would expect from ordinary Minkowski space-time. So, allowing for this, let me get beyond that, okay, and assume that these are straight lines. Still, the main thing is that if we ask at the time of decoupling, when photons no longer interacted with barriers and were left to move unimpeded until us, at a time which is about redshift 100, the size of our horizon had a certain extent, which had to do with the time that this occurred in the past universe. And any point within this hypersurface had its own horizon. If we go back, say, to time 0, but here, you can put here Big Bang nucleosynthesis time. We know that at least something has happened at some. Remember that the scale factor, which is what I'm using as time variable, it just simply tells you what was the size of the horizon, or size of the universe at that time, essentially what is the energy content of the universe. So we can parameterize time as scale factor or as a function of the density. So the only thing we know that before the photon decoupled, there was a time, Big Bang nucleosynthesis for instance, where there were many patches which were completely disconnected from each other at that time and still provided properties for the time of decoupling, which we will see are identical to each other. And this is the problem of what's happening. So remember, in a universe which is expanding, dominated by radiation matter, and we know that has happened since Big Bang nucleosynthesis, first radiation and afterwards by matter, the scale factor is growing as a power of time, cosmic time with a power which is more than 1. So the universe is decelerating. The radiation, t to the 1/2, the matter, t to the 2/3. Okay? So this deceleration means that essentially the horizon is moving faster than the size of the universe. Okay? So imagine that at time of decoupling, the universe had a temperature of 0.3 eV. There were many Hubble radius, or horizons, which were, in principle, causally disconnected. All these different patches didn't know about each other. The time had not been long enough so that information would have gone from here to here to tell you guys, put yourself in the same state as I am. Okay? So let us evolve from the time of decoupling until today, at 3 Kelvin, and let's ask what happens to our Hubble radius at decoupling. It's clear that all of these will also grow. The horizon is growing faster than the scale factor, and I'm describing the scale factor as the radius of this sphere. So imagine the universe for us is this sphere. We just happen to leave and put ourselves at the pole. The horizon is growing fast. This balloon, which is our universe, is growing much more slowly. That means that the horizon will very quickly cover a much bigger area. Well, today, the horizon has covered essentially the whole size of the universe. H naught is of the order of 8.1. A naught is -1. And therefore, all these regions which were causally disconnected at the time of decoupling are actually within our horizon, and we can measure. We can observe what are the photons coming from this region and the photons coming from this other region, which in principle didn't know about each other at the time of decoupling. Of course, they didn't know about each other even at the time of Big Bang photosynthesis, where the horizon would have been much tinier. Now, the fundamental question, the consolidated question is, how come the photons that we observe from this region and this region have exactly the same properties, the same temperature? So if we look in different directions, and we don't have to say opposite directions, it's enough to anything which is beyond a degree in the sky, they were not in causal contact. Let me go back to the previous. They were not in causal contact. Right? These two regions did not know each other. They were passed, not crossed. So how come all these regions have exactly the same temperature to within 1 part 10 to the 5, where fluctuations are observed? If you ask how many causally disconnected regions are at that time for quality, this goes like 1 plus redshift during matter radiation to the 3 house. So if we substitute here decoupling 1100, then we get something at 10 to the 5 disconnected regions. So in the sky, there are 10 to the 5 disconnected regions. Again, anything which is beyond 1 degree didn't know about each other at the time of decoupling. So let me draw this, again with figures similar to that. The scale factor grows like t to the 1/2. It's decelerating. Its slope is more than 1. During radiation and matter, the horizon grows like time, 2 times, or 3 times. Time, 3. And therefore, we can ask, if we look back, today the universe is essentially the size of the horizon, h-1, essentially a0. Okay? So we can measure back and ask, at the time of decoupling, how many regions were comprised within our universe, and if this is the size of the causally connected region, it's clear that the size of the universe is much bigger, and the factor from here to here is 10 to the 5. Okay? It is in these scales. So if we go further back to the universe, it was always, we're talking about radiation and then after matter, it was always much bigger than the size of the horizon. So there was no physics which allowed us to bridge this gap and make all that we observe today actually be in causal contact, except if something happened very close to the Big Bang. And this is where inflation comes. It's going to modify the early units, it's going to modify here this period. Right? So that what we gave our notions of Big Bang, the moment we produced all the radiation in the matter, was much more complex than we thought, and we have to extend that to minus infinity. So the very elegant and most simple solution to this problem comes through inflation. You will see that inflation is not just a period of exponential expansion. I'll try to convey here. It's extremely rich. You will see through the end of inflation, even through the peculiarities of the matter fluctuations during inflation, that we might have today observations that will give us a clue of what happened in the very early universe, before the Big Bang. So for us here, and this has happened in the last, I would say, 20 years, there will be a reassignment of what we call Big Bang, not to the moment where the whole space-time was formed, at time to minus infinity, what quantum gravity associates with the initial state of the universe. We will call the Big Bang the time of the formation of all the energy and the matter in the universe today. Okay? This is a real time. We're going to differentiate between the formation of space-time itself. I was describing before in quantum gravity, how did the space-time pop out of nothing, okay, to the formation of the energy content, matter and radiation. We will call that the Big Bang. That's the actual Big Bang of Lemaitre, back in the 20s of the past century. So for us, the Big Bang will be this time, and it was. So inflation is pre-Big Bang. So let me describe this. You're all familiar with Mr. Heisenberg, okay? Famous relationship. You could multiply by c both sides, h bar c 1. This is energy and this is x. That means that 200 MeV times 1/3 to the bound is a order 1 for quantum phenomena. That means that we can relate high energy phenomena with small scale physics. You're all familiar with this from quantum mechanics. The immediate application of this is that particles can be created out of the vacuum. And we are very familiar with this. The polarization of the vacuum, which gives rise to the renormalization of couplings. Essentially, the electromagnetic coupling is not the same at any scale. If we probe sufficiently close to any particular particle, the charge of such a particle will be modified because of the fact of this pair creation, which polarizes the vacuum. Okay? So particles are created. We are very familiar with this in particle physics, doing experiments in high energy particle accelerators like LHC or Electron and any other previous experiments there, etc. So the production of particles out of the vacuum is well known. But imagine you have a space-time on which phenomena occur. Photons, electromagnetic charges like electrons, quarks, etc. So we can pop out on space-time as a background, we can pop particles out and they modify electromagnetic properties, for instance, of space-time. Now, it's not inconceivable that similar phenomena like this might happen not just locally in space-time, but in space-time itself. Perhaps space-time is no longer the smooth manifold on which phenomena occur. It could happen, and for this we need, of course, much higher energy phenomena than we are discussing here for the production of particles like electrons. Here you only need a few MeV. In order to pop out space-time regions out of the vacuum, you have to subministrate much higher energies of the order of quantum gravity phenomena, that is, at the level of Planck scale. So the sort of scales that we will reach that are amenable to exploration with present observations will reach back perhaps to grand unified theories scales, 10 to the 15 GeV. Planckian scales, quantum gravity, reaches even further up, 10 to the 19 GeV. So it is possible that eventually, by looking at phenomena very early on that now appear in our horizon, we might be able to connect with the with the previous epochs. However, at the moment, we don't have any evidence at all of this quantum gravity phenomenon. But it's perfectly possible within the theory to describe this creation out of nothing of the space-times, and it is possible that simply our universe came out of a quantum fluctuation of space-time. So this, I insist, would go to minus infinity. We're not going to deal with this here. So if a small bubble of quantum vacuum was popped out of nothing and expanded very rapidly, this would have very quickly covered the full space-time. Very soon, such a little object would have grown to be as large as our universe, or even larger, in this global structure of the universe that I was describing a while ago. Okay? So what do we need in order to provide this? Well, first, we have to have some kind of energy density popping out of the vacuum, just like we produce particles. Electrons and protons out of vacuum particle accelerators. And it's perfectly possible that that vacuum energy is close to constant. Now, how did we produce such a vacuum energy out of Planckian scales? It's still a mystery. We don't know what is the origin. Moreover, in order to describe inflation, the only thing we need is an approximately constant energy density, which is more or less homogeneous. That doesn't mean that on very large scales it will remain to be homogeneous. I insist, at distances of trillions of times our Hubble patch, it might be extremely homogeneous. Okay? The only thing we need is within a given patch of space-time within the horizon, the energy density to the approximate common changes. Now, that doesn't mean we understand the physics responsible for this vacuum energy. It could be an effective description in terms of a scalar field, like I'm going to describe, scalar field theory, but that doesn't mean that the fundamental description of inflation is that of. How am I doing with time?
Just 45 minutes.
Just 45 minutes? Then I should stop here.
Thanks.
Let me end with a few instances. So this vacuum energy, we're going to describe in terms of some potential energy. This is an effective description in terms of the scalar field. This scalar field could actually be a composite, just like we know for superconductivity. We could describe this by the usual Lambda-Ginsburg model. It might have some internal dynamics, like the Barley-Kudler-Schreier description of a hole and electrons, which gave rise to this effective description. So we're not going to deal with the fundamental description of inflation. We're going to deal with the effective theory of inflation. Okay? We're just a scalar field. It's enough to describe the whole evolution. So I'll stop here. And questions so far? If I go too fast, please stop me. If you get bored, also stop me. Tell me to go faster. I'm sure I'm just very slowly gaining momentum. Right? It will get faster. So if you feel you lost something, tell me.
Sorry, and maybe with
Yes.
one instance that goes back to minus infinity.
Right.
On refunds.
Yeah.
Inflation.
That's right.
I
Are you asking why?
I just missed. I really missed. I came a bit late.
Right. Well, at the beginning of the lecture, I was describing the whole timeline, which we're used to in cosmic time, and comprised 13.7 billion years. That's a distorted image from the point of view of modern cosmology. So we have to understand what goes on today as a mapping between what happened before the end of inflation and what happened after the end of inflation. The whole of cosmology deals with what happens after the end of inflation. But we know that there are connections. There's this one-to-one mapping. So what happens before the 65 epochs of objects that we now observe within our horizon? We don't know. Simply because we don't access anything that goes beyond our observable patch. But that doesn't mean it's not there. Right? We are aware that, at least extrapolating the physics that we know of inflation to much larger scales, stochastic inflation, we can deal with questions: what happened in the far past to time minus infinity? We can ask, where did our patch actually come from? Is our patch a particular instance of a much bigger realm of a multiverse, or can we really trace back this little patch all the way to minus infinity? This is a question which can be posed in GR. It has been done by Guth, Borde, and Vilenkin. And this suggests that we can find any given patch in the universe would have a geodesic, a complete geodesic, all the way to some distance which can be traced all the way to minus infinity. Not all of those can go to minus infinity. Right? Some of these will find a singularity much before you reach minus infinity. And that's the theory that these people obtain. But there are some that you can move through, some geodesics, which you can trace back to the visual instant. Now, what that instant is, we have
one isolated.
in conformal time. Excuse me?
Only one isolated.
Only one isolated. That doesn't mean that there are no further other possibilities. Out of the quantum vacuum, you can produce bubbles that created their own meta-universe, which were completely disconnected. Okay? We might happen to be connected through space-time to regions which are very different, have very different physics from us, but even still, this could be very different from, again, another instant where quantum bubble formed and have no connection whatsoever with us. So let me draw this. Before the presence of proper space-time, this could be a sea of fluctuations. Okay? So one of these could start and produce some growth where there's enough energy density to drive the expansion, local expansion of the scale factor here, and this will grow to become our universe. Eventually, such a universe will have observers that can look back to its past. But that does mean, of course, that this observer has within this patch properties which are different from these other observers. These universe that we call our universe, which might be traced back to this will be not minus infinity, in space-time slice. if you could describe classical spacetime in a way here, they may have nothing to do with another possible instant, and this requires quantum gravity. I was describing at the beginning. You have to know, and this is the main difficulty with stochastic inflation, giving the proper measure of the probabilities of one of these events happening. That's the main difficulty nowadays of quantum gravity, finding the proper measure, how to assign probabilities for the creation of universes out of nothing. So it might happen again that another spacetime was formed completely disconnected from this one. That doesn't mean, I insist, that the properties of these two universes, which might have, say, other observers at a different time, which have gone through a different period. For instance, it might happen that this has its own hypersurface of Big Bang, formation of all the matter and the radiation, at a different time from us. There's nothing wrong with having this in this picture. It could be completely different from the future evolution of such an event. So, for the moment, we don't have the proper theory to account for the probabilities of finding ourselves within this scheme and differentiating ourselves from this. With the stochastic inflation, we can trace back from observations that we have here back to some early time, and then see how does this could ramificate, so create trees and produce universes with different properties than the one we observe in ours. This could be a meta-universe. But I insist, these are different from other events coming directly from quantum gravity where you pop up. The universes have completely, radically different physics. So it's clear that from our human standpoint, 13.7 billion years after the Big Bang, in the effective description that, like the one I have given you, we don't have enough power to answer such fundamental questions. Okay? It would require to understand through those observations, through this mapping that I was saying at the beginning, from the early universe to the late universe, trying to see whether we could infer from that mapping. For instance, we observe gravitational waves in the polarization of the CMB, which, if we could infer what was the physics much before those 65 equals. Okay? So trying to probe, sneak in the properties before the 65 equals, closer to the Planck time. But that, since we are in logarithmic scale, will require hard work. For the moment, we don't have such a vision. Okay. Any other question? Yes?
It might be a bit too soon to ask, but I was wondering if you could say more about this one-to-one mapping you mentioned. Is this a mapping of observables to causes in the universe?
Yeah.
It's not a mapping of sort of geodesics in space?
It's a mapping of geodesics, in fact. You will see that phenomena, different energy scales, the phenomena that occurs in the early universe before the end of inflation, will have a mapping through geodesics.
Right,
that means
space-time mapping.
A space-time mapping.
Yeah.
That's right. It's not just a mathematical mapping of phenomena, it's also a space-time mapping. You will see that certain patches of the universe before inflation will have properties that will determine what happens after inflation. For instance, something that I will deal with in the last lecture, primordial black holes. If something occurred during inflation, something that the scale factor slowed down, okay, and produced a peak in the Planck spectrum, this will have consequences when that peak re-enters the horizon during matter that will form to collapse black holes and perhaps produce the dark matter we observe today. So things that today we treat as observables might have some properties that actually correlate with what happened in the early universe during inflation. And this one-to-one mapping will allow you, by measuring today, infer what was the dynamics of inflation.
So if you fix your initial theory of inflation, then there's a one-to-one mapping from there to the future. But if, say, you are ambiguous, you don't know about it, and you start today, there's no mapping back, right?
Well, this is true with inference in, this is epistemology, right? In the philosophy of science. The way science works is by making hypotheses and saying, look, if my conditions were such that this such and such property occurred, then I can infer from here that I would observe such and such a thing. Of course, going backwards, it's an inverse problem.
Yeah.
It's not always unique. Okay? So it might be that the dark matter has nothing to do with primordial black holes, and therefore you cannot correlate what we observe today with what happened 20 equals before the end of inflation. Okay? But that's within given theory. Right? So you work within a theory, you make hypotheses, and you ask what are the consequences of this hypothesis. Okay? Of course, the more hypotheses you have tested, The CMB is an extremely rich place for searching for signatures of inflation. Okay, you can search for non-Gaussianity, you can search for the spectral index, you can search for the statistics, etc. All those things are going to give you a property that you can try to correlate with what happened in the unit during inflation. Now, there might be some properties which are correlated, and these will give you clues. For instance, if we find gravitational waves through the polarization of the CMB, and we compare their amplitudes with the tilts, we might have this consistency relation, which in any other theory, except for inflation, would not have been related, and here they are. So if you observe such a correlation, then at least you have good argument to suspect that something like inflation must have happened in the early universe, otherwise you would not observe what you observe. Okay? Same would happen with parabolic black hole. If in the future, and fortunately here you are in a very special place with a square kilometer array, you might be able to test what happened since reionization of the universe, what happened when the first structures formed, the first stars and galaxies formed. Why? Because the rate at which that structure formed is going to be very, very sensitive to the agents that created the structure. If this was not ordinary matter and baryons, but you had primordial black holes to see the structure, then the rate at which reionization will occur is very different. So we're going to have windows into the universe in the near future, 10 years from now, with SKA that will open up completely new paradigms, new scenarios. And it will test all these hypotheses. So I want to insist here, we have much further connections than we envisioned 20 years ago. Now we understand that things can be accessible through observations and make connections to the early units before the end of inflation, which before we had no clue of. Okay? Other questions? Okay, so let's stop here, 5 minutes, take a rest, drink some water, and come back. We don't know what is the fundamental dynamic responsible for inflation. Okay, the only thing we can do for the moment is make hypotheses about certain dynamics. This could be suggestive of some high-energy physics, for instance, fragile physics, of which we have no clue today. We do not see any of these phenomena in particle physics accelerators, a fundamental access to it during experiments on Earth, but we can infer, we can try different hypotheses. Okay? Remember that cosmology is very special within the realm of other sciences. This is not an experimental science. We cannot reinitiate our universe again. We have to infer from what we measure how was the universe behaving some early time. This is more close to evolution in the theory of biology. Okay? So you might argue that there's a fundamental paradigm, that's inflation, describing the connection, and I'm going to describe this one-to-one mapping between the early universe and the late universe, which is similar to what happens in evolution. You have a fundamental principle, and this fundamental principle gives rise to a fantastic variety of phenomena. And here we're going to see that this fundamental principle, it's very robust. It doesn't depend very much on the dynamics. We can change the dynamics and see it's true. Different inferences, we can determine properties which are different from one model to the other, but still the fundamental principle that there is a vacuum energy approximately constant which drove the tremendous expansion of the universe still remains. Okay? If you want, this is similar to the gauge principle in particle physics. Okay? We know that there are fundamental interactions, those particles or fundamental fields should be related through gauge transformations, but we don't really know what is the gauge group corresponding to our theory or to our observation. So we have to assign from measurements the concrete gauge group. Okay? We happen to see within particle physics that our group is very peculiar. SU3 for strong interactions, SU2 for the weak interactions, and U1, the remaining one, for the electromagnetic interactions. But this was not like this in the past. It's actually probably related to some grand unified group. But still, the fundamental principle is still there. Gauge invariance is the same, whatever the group. Okay? We have to only measure today, determine the group, and try to infer what was the group much further back. Same happened with inflation. We know that something like inflation might have happened. We have enough information from the CMB, logical structure, etc., to infer that such a phenomenon occurred, but we don't know what its dynamics. We have to deduce its dynamics from measurements. Unfortunately, and this is where the mapping that I described at the beginning is relevant, we have access to inflation only in very tiny windows. We can access inflation, say 65 to 55 epochs before the end, by measuring logical structure and the CMB. But we don't have any access about inflation until very recently, say 20 epochs before the end of inflation, or right at the end of inflation, when the universe reheating and the Big Bang started. So during the last 15, 20 years, we have been exploring the physics, the very rich phenomenology that inflation provides, for instance, at the end of inflation through reheating, and trying to see whether things that we observe today, gravitational waves, primordial magnetic fields, black holes, could have something to tell us about the early universe before the end of inflation. Okay? So it's true that it's a very weak connection. Fortunately, the model of inflation is sufficiently simple that we can correlate within that model properties of what we observe today. For instance, the amplitude and the possible tilt of a scalar in tensor fluctuations. This is going to give us a clue. Or, as I will describe, the mass distribution of primordial black holes, which could influence the dark matter. Perhaps those correlations are actually telling us how did the universe behave before inflation ended. Okay? So I'm going to open to you, this is the purpose of these lectures, 4 lectures, open to you those windows and suggest to look into those windows looking for signatures that might tell us what happened there, where we don't have particle accelerators to probe directly. Okay, so we were describing here, if we have a vacuum energy which is approximately constant, I'm describing this like a plateau here, this scalar field, I insist, effective description, it could be anything apart from the scalar field. We don't even know, by the way, the only scalar field that we have ever measured, which is the Higgs, is a fundamental particle or not. We might happen to be at too low in energy, so that the internal structure of the Higgs is not yet accessible. Okay? We might have to reach energies hundreds or thousands of times those that are explored nowadays in particle accelerators to probe the inner structure of the Higgs, if there is any. Maybe it is a fundamental structure. So the same happens with inflationary. Okay? We're going to treat it as an effective scalar degree of freedom. We're going to follow, within the rules of GR, what is the behavior of such a scalar field. Okay? So we know that there is some period during which the scalar field evolves slowly. We describe the snowball. Eventually, these will start accelerating, will end inflation. There is a moment in which such tremendous energy density due to this vacuum energy will end and will convert all that energy into radiation and matter. This is called the reheating of the universe. It's a fascinating phenomenon. It has tremendous consequences for our observations today, and I will describe a few of those. Some you will find much further described in the lecture notes that I pass on to you. I will give you a very broad view in these lectures, in the oral presentation. Okay? So the main thing is that this vacuum energy is going to convert itself into radiation matter. And we're going to call this the Big Bang. Okay? For us, time is equal to 0, or if you want, the scalar factor equals 1, is the end of inflation. That's the Big Bang. All that Friedmann thought of would correspond to the end of inflation. It's true that in different regions of the universe, the Big Bang will happen at different times. For our patch of the universe, at least, we know when the Big Bang happened. Okay? The time where all the radiation in the battery of the universe arrives from the decay of the inflaton. But in other regions of the universe, at tremendous distances from our solar universe, it could have happened with different time. Okay? So it's important for you to realize this within the global structure of the universe picture. Okay, so the most obvious thing that such a vacuum energy produces in the context of general relativity is a tremendous growth of the size of the universe. So again, let me describe the universe like a sphere. If we ask what is the size of the horizon within that sphere, that's a very tiny patch. Okay? So our universe is filled up with dark energy. Today, vacuum energy, inflation energy in the past. And this vacuum energy accelerates the expansion of the universe so fast that within a few eFold, the curvature of the universe becomes 0. That doesn't mean that it's 0 on all scales, obviously. If there was any scale initially, it would still remain with such a scale some distance from us. It's clear that if we go much further away from this horizon and we ask what would happen to the universe at very large distances, it might still contain some kind of curvature. For the moment, the only thing we can measure today after such an expansion is that the spatial curvature is exponentially small. This might explain those peculiar initial conditions at the time of the Big Bang synthesis that I was describing before the break. Okay. So this is what happens for space-time in detail, and this is within the lectures. you could characterize this with a scalar effective theory. So this would be a scalar, your dynamics characterized by this potential V. You can write the Hamiltonian momentum constraints coming from invariance of the action under reprioritizations, which relates the rate of expansion of the universe with the matter content. In this case, we're assuming there's only one kind of matter, and that's the scalar field. Okay? Eventually, that scalar field will decay the rest of matter, radiation, particles, quarks, electrons, gauge fields, etc. All that we observe today. But at the time of inflation, this is the only field which drops. And you might ask, wait a minute, what are the other fields? The other fields are quantum fields. They should also pop out of the vacuum, as we were describing before the break. Now, why aren't they there? Well, they are there. Okay? It's obvious that the inflaton is coupling to the rest of the fields. The thing is that these particles, they're very different from the scalar field. These particles have, when you produce them, they have essentially no mass. There are tremendously high scales. Those objects will be redshifted away, their energy density, like radiation. This means that within a few e-folds, the energy density which goes like 1 over the scale factor to the 4th, very quickly will disappear. In less than an e-fold, the amount of energy which is damped from the inflaton into those particles is redshifted away. So we can, even though there is a tiny production of particles, we can ignore them at any time, because they will be redshifted away. Except, as I will describe in the last lecture, if there are certain properties which are exponential growth of some of these gauge fields, which could back react in space-time. But let me postpone that for later. For most cases, any particle which is produced during inflation through the coupling of the inflaton will be redshifted away. Okay? So the only field that we will be dealing with is this effective scalar field. The potential which is self-coupling of the field. Okay, you have also the momentum constraint and the evolution equations. How quickly the rate of expansion changes and the evolution of the scalar field. In final notation, this is the conjugate momentum of the field particle. Okay, if we take into account the constraint equations, we can convince ourselves through renormalization invariance that the dependence, explicit dependence on time, cosmic time of the rate of expansion is 0 when phi is constant. And the momentum of the field is also constant when phi is constant. And therefore, you can write the rate of expansion just as a single function of the scalar field. Okay? This is very fundamental. Nothing to do with any theory of gravity. As long as you have renormalization invariance through the Hamiltonian and momentum constraints, you know that this function cannot depend exclusively on time. It can only depend on time through phi. And this is great because we know in GR, once we have a field, we can always do redefinitions of space and time. So we will use phi as our time coordinate. We'll use phi as our clock. And phi is going to characterize, with its energy density, at what moment are we before the end of inflation. So when we say 60 e-folds before the end of inflation, the fluctuations that we observe in the CMB today were produced, then we're actually telling what was the value of the field phi at that time. It's a clock. It's a one-to-one correspondence. Yes? No? Okay. I thought you had it. Now, if this is true, then the Hamiltonian constraint becomes a very simple equation. It's called the Hamilton-Jacobi equation. And it relates whatever dynamics we may have with this function h of phi and its derivatives. Once we have h of phi, we can compute phi dot and h dot automatically. There is no time dependence. Okay? It's just simply variations of h with respect to phi. It's so simple. This is well known for usual Newtonian mechanics, theoretical mechanics, okay? Hamilton-Jacobi equation, and it's applicable also during inflation. This means something very interesting, which is that we can deal with inflation in a simplified way. Why? If we come to the Hamilton-Jacobi equation and we find an exact particular solution of this equation, okay? Here in principle, this field could be even inhomogeneous, okay? And then we make a perturbation of this particular solution. We ask, how can we deviate from this solution? And we write this as a perturbation in the only function we have, which is h. And we ask to linear order, how does the Hamilton-Jacobi equation evolve? We find this equation. To linear order, we've dropped terms like delta h squared. But this equation can be integrated, okay? So the fluctuations will be whatever the fluctuations were at some initial time times the exponential of this point, which we can write. It's always a negative quantity, you can write it this way. The expansion of minus 3 times the variation in the number of equals, the same number of equals that we have here. Although here the scale factor could depend on both space and time. That's important. Whatever these fluctuations in the number of equals, it's clear that if we started with some perturbation very quickly, if in a few equals, where n I minus n is delta n, so it's positive, in a few equals you will go down to 0. So all fluctuations dump out. This is what the Hamilton-Jacobi are telling me. Whatever your initial conditions, all fluctuations are dumping out to this particular exact solution. So this exact solution is a single trajectory in phase space. So before this analysis, you could have initial conditions in the field and the derivative of the field, or the field momentum. Remember that we will soon quantize this system, and the field and the momentum conjugate are independent quantities which satisfy quantum commutation relations. Okay? So it's very important that during inflation, whatever the initial condition in the whole map of initial conditions in phase space, phi dot, those trajectories will end up in a single trajectory. So phi dot, it's only a function of phi. We don't have any messing up with time. It's just simply a function of phi. Okay? And this is crucial. If we happen to have just a single trajectory, we know exactly when the end of inflation will happen. We know, therefore, how many EFOs, the quantity that we can infer from here, how many EFOs happen from the end of inflation backwards. That's why this mapping makes sense. Otherwise, it would not make any sense. Okay? If we make fluctuations of such a space-time, and we ask how did the universe behave, say n EFOs before the end of inflation, we have a one-to-one mapping to the value of the field phi, and therefore to the dynamics of the field at that time. Okay? This is crucial. It's called the slow roll attractor of theory. And thanks to that slow roll attractor, we can deal with what we call the slow roll parameters, which are a single quantities derived from variations of the rate of expansion with respect to the field, which characterize the trajectories. Epsilon and delta are going to characterize to linear order, first order, all the trajectories. And this will be crucial in order to find the fluctuation, quantum fluctuation. Jose, you had a question.
So, in this previous argument,
Excuse me?
the previous argument you were making,
Yes?
it's only if you have a standard kinetic term, right?
Standard kinetic term.
For the scalar field.
You could always redefine your scale field. There's a one-to-one mapping again through a redefinition of fields. In the quantum path integral, it's simply your measure that should be variant under any field definition. What that does is change your dynamics. So the previous expression, it's valid. Oh, sorry, I should go in the opposite direction. This is valid for any dynamics. Okay? And you're right. This is only, this is from this kinetic term. If you change your fields, you have f of phi here, you redefine your field, and then you have, say, some var phi, you have another dynamic.
I was thinking of P of x.
Excuse me?
I was thinking of P of x. So, for instance, add P phi to the 4.
A function here of both phi and p of phi. Yeah?
No, P of x. P of
X being the derivative of phi. Again, you could always find a redefinition of fields which will change your dynamics and will show you a different potential. It's one-to-one. Unless it's singular. In some cases it might be singular. But in most cases, okay, we can just scan this out. Okay, so once we have this scalar field, and we have its dynamics through the Hamilton-Jacobi equation given in terms of the rate of expansion as a function of phi, then we can compute those quantities, which I'll show you in a minute, are relatively small, and therefore we can treat as perturbation parameters. In that case, our field phi will act as a new time variable. Again, in GR, you could always redefine time and adjust to whatever quantity you can use in order to characterize the space, spatial hypersurfaces. In particular, this new time, the number of EFOs, is written as a function, an integral over this phi time. So, knowing the dynamics and its derivative, you can infer out of the scale factor curve and the number of EFOs. Okay? So this will tell us this n that we were using all the way to today. Okay. So, in this slow roll approximation, taking these quantities to be small, epsilon and delta, the full equation, which is h squared 1 minus epsilon 3 equals this, in the Hamilton-Jacobi equation, becomes essentially h squared equals phi, phi. So we have now a first approach to the attractor. Okay? The same happens with phi dot. It can be written as minus the derivative of the field, over h. These quantities in this approximation, where you only sensitive to the dynamics, v of phi, will give you, in the first approximation, v prime over v squared epsilon, which should be smaller than 1. Delta will be written as some quantity which has to do with not the first but the second derivative of the field, if you want the mass of the field at any point in time, or value of the field phi in time, and we call that eta minus the same quantity we had defined before, minus epsilon. So this again should be much more than 1. You could go to all orders. You could go to higher derivative terms, okay? Third derivative, fourth derivative, etc. Okay? We will see at the end of this second lecture that the growth of perturbations will be extremely sensitive to these quantities, epsilon, eta, psi, etc. And these quantities are going to give you information about the amplitude and the tilt of the fluctuations in the curvature that eventually will become fluctuations in matter and radiation, which we observe from CMB anisotropies. So, knowing the dynamics, we infer parameters that will be measured. Okay, so we found something that we can measure. Of course, we were talking about one-to-one mappings. From the measurement of those parameters in the late universe, we can infer what kind of dynamics produce them, but there's a whole array of possibilities which are consistent within the errors of those parameters. So there's always an uncertainty, what is the dynamic during inflation? Because we're not seeing the full potential. We're only observing those parameters at a given instance. Remember, these are quantities which depend on phi and therefore depend on the number of EFOs at that time. If we explore only a few EFOs before 65 in the CMB, we're only going to look at the shape of the potential in a given window in phi. Remember this? So we're not going to get from the CMB the whole evolution all the way to the end of inflation. Okay, that's an extrapolation. And it's a very dangerous one. Because it could happen that during inflation, say some EFOs before the end, new dynamics arises. These fields could couple to some other fields and change completely the picture. In particular, produce, as I will describe in my last lecture, primary black hole. Okay, so in the same approximation, the number of EFOs can be written in terms of the derivatives of the potential. Your energy density and pressure for these homogeneous scalar field has its own conservation equation, where rho and p are very closely opposite to each other. The deviation from each other is just over phi dot squared, which is very small compared to the dynamics, to v of phi. And therefore, pressure and density are almost opposite to each other, which within this equation means that rho is approximately constant, h of phi is approximately constant. Okay? Now, if h is approximately constant, we know through Einstein equations that the scale factor is going to grow exponentially. Great, because that's all we needed. Remember to solve the horizon and the flatness problem. First, let's concentrate on the flatness problem. Imagine that we ask today, what is the value of this deviation from 1 of omega to omega? Okay, normalized to omega. This is some initial value before some time during inflation and large infinity. The exponential expansion of the universe, remember this quantity x went like some constant over the density times a squared. The density you see is approximately constant. So the only quantity which evolves there is the scale factor. It's in the denominator, so you have e to the minus 2 times the number of EFOs. And therefore, the more EFOs we have during inflation, the closer to spatial flatness. That's not surprising. Remember the figure. Here we go. The more EFOs we have, that is going to give you, if you want, the size, the curvature size of that universe. The bigger the number of EFOs, the larger the extent by which the scale factor has grown, and therefore the more flat the universe is. And this you see explicitly in terms of these expressions. So, assuming that the universe reheated very soon after the end of inflation, if not, you have to take into account a factor here, which could be a 4 to 1. We're going to ignore it for the moment. The universe reheated at some high temperature, very high temperature, when you could release all the radiation and the matter, and it would go through radiation epoch until matter radiation equality, T equality, and then you go through matter epoch. Now, if you put in here numbers, you find that e to the minus 2 times the number of EFOs during inflation times this growth, tremendous growth, 10 to the 56, should be smaller than 10 to the minus 3 or so. square should be greater than 10 to the minus 3. That means that n should be at least bigger than 65. Simple computation. And this is the origin of my connection. Okay? Here n equals 0. Whatever happens before 65 equals is going to follow the same one-to-one correspondence. The number of equals that occur here are identical to the number of equals that occur after inflation. It's the pivot point. The end of inflation is going to correspond to a place where 65 equals before the end, scales went out of the horizon. 65 equals after the end, they re-enter the horizon. It's as simple as that. There's going to be a one-to-one mapping. We'll see that scales that left the horizon 65 equals today have entered, and those two are correlated. And we'll see through physics or geodesics of those patches, which will connect those. Among others, if you have such a large number of equals, it's easy to realize that the free curvature of spatial hypersurfaces, right, very quickly goes to 0. The energy density of matter goes to 0 very quickly. This is the reason why we can ignore radiation in matter during inflation. Okay? In a few equals, they're gone compared to the energy density of the inflaton, which remains constant. Remember, during inflation, the energy density is approximately constant. And these are not. Very quickly go away. Curvature in the fluctuations of the scalar field, which are related to fluctuations of the metric, will also go very quickly to 0. Okay? Fine. So far, I have described to you the background evolution. All this connection between early and late universe are connected through the background. Okay? Patches that occur earlier would correspond to patches that appear later. There's space-time patches. But of course, physics occur within those patches. Okay? So there will be fluctuations. We know that we're dealing with quantum fields. Classical space-time is a limit of a fundamental description in terms of quantum fields. Among others, this is scalar field. Even if it's an effective scalar degree of freedom, just like the pi, you can work out the Yukawa theory of params and treat them as quantum fields. Protons are composite particles too. Yeah, they're made out of quarks themselves. Can be treated as quantum particles, and you can construct creation and annihilation operators. So I'm going to do exactly the same for the inflaton. So the inflaton for me will be a quantum field, whatever its internal structure, as long as the energy density that can probe is not hard enough to open up the structure. I can ignore the properties, fundamental properties, quantum properties of that field. So I'll treat this as an effective field, which is quantized. You can quantize this by doing perturbation theory. To linear order, at least for the beginning, you can go to the second order later on. To linear order, if you compute your space-time structure, here I've put all the timing conformal time, I've put the scale factor outside the metric. I've taken a flat metric, a space-time metric. There's no free curvature here. So Hij would be the fluctuations, not on curvature, but on a fluctuation on which propagate in the metric. They are the tensor fluctuations, which will give rise to gravitational waves. And I will assume that there are no vector fluctuations. I will not go into the details of why not. Vector fluctuations in the context of inflation are subdominant. The reason being that since the amplitude of the scalar field is very tiny, the source for vector fluctuations goes like the square of this amplitude. And this is completely irrelevant. There is no source for vector vorticity during inflation. Okay? That means that the only two modes that can grow during inflation are the scalar and the tensor without any vector. That's in agreement with what we observe on very large scales in the CMB and on large scale structure today, so we think it's a very good assumption. Okay? So at least from inflation we have a realization of fluctuations that are in agreement with what we observe in the late universe. If we treat only the scalar fluctuations and the tensor fluctuations, these are the linear perturbation equations. They look very messy. Fortunately, people like Slava realize that there is a combination of quantities. The field phi fluctuations, this is your inflaton fluctuation, which gauge invariant fluctuations, and your scalar metric fluctuations, which together with this background quantity, denoted by Z, the combination of the scale factor and the time derivative, the background of the field phi over AH, or if you want, of the rate of expansion in conformal time for the expansion of the universe. This background variable times phi plus the scale factor times the fluctuation becomes a U quantity called the Juan variable, which has an extremely simple differential equation. We'll go for more time. This is an equation that you can associate with a, let me see where I have it here. No. This is nothing but a Schrödinger equation. Okay, if you write it properly, and it's in the notes, you can see very clearly this would be, if you substitute time for space, and you go through mode equations, you expand this in terms, as I will do in a minute, into plane waves, then this would become your energy, and this would be your potential. So once we solve such an equation for a given background evolution, we can automatically determine the amplitude of those fluctuations. Yes?
We are running out of time.
We're out of time? Yeah. How much time have you got?
It's already...
It's only 2 or 3. It's only 2 or 3 transparency. Okay, so those quantum fluctuations have their own action. That means we can quantize the field, creation and annihilation operators. They satisfy the usual Fock space relations. Notice that in linear order, this is crucial. Each of those fluctuations are independent. There's no mode coupling because the amplitude is small, and we can treat quantum field theory as an infinite harmonic oscillator quantum mechanics. Okay? Each one of those modes will behave independently. So we can write Fock space vacuum, which is annihilated by the annihilation operators, use equal time commutation relations, and derive from here the initial conditions for the evolution equation of the mode. This can be written like a Schrödinger equation. This would be energy. If you multiply by h bar squared over 2n, it's nothing but your Schrödinger equation with the potential, which is time dependent. And this is the key issue. If the potential is time dependent, then your Fock space is not well defined. Okay, this is crucial. Imagine that you have in quantum mechanics, you start with a wave function. Maybe I should describe this in a little bit in detail. Even though I have a few minutes, I think this is important to emphasize now, not only tomorrow. In ordinary quantum mechanics, if we have a potential, this is my field U, and this field has a ground state. If the mass of the field, or the potential, which is what we have here, is not constant, your wave function will vary. Imagine that you have now, sometime afterwards, this mass becoming larger in the usual adiabatic approximation of quantum mechanics with time-dependent potentials. The new vacuum would have a different ground state. It just simply evolved from one ground state to the other. If this is adiabatic, so very slowly the potential changes, its mass depends on time, very slowly, you will still remain in the vacuum. You will go from one state to the other. This would be with side 0, this would be side 0 prime, and it would be adiabatic. However, during inflation something very peculiar happens. That is that expansion is so fast that this growth of the mass squared of that field is exponentially fast. That means that there is no time for the wave function of each one of those modes to adjust to the potential. Then suddenly they appear. There's a very quick growth of the potential. So you have the whole tower of the states being probed. And when, again, this field has a mass which decreases, this goes very fast and then decreases, suddenly you find yourself populating the very high excitation modes of the field. When the field relaxes back to its vacuum, you will end up, that is after inflation, you'll end up with the vacuum full of particles. These particles, quote-unquote particles, excitations of the field, are what is going to populate space-time. Those are the modes that we measure like curvature fluctuations in space-time. So it's a purely quantum phenomenon. It's due to non-adiabatic, or if you want, the sudden approximation, right? Like we do with potential barriers, okay, very quickly changing in time. You populate all your states in quantum mechanics. I'm sure you're all familiar with that. When you go back to the ground state, you'll find that your ground state is not empty, it's full of particles. This creation of particles out of nothing, okay, here is out of the expansion of the universe, takes energy out of this exponential expansion. So it's producing particles, which here are curvature fluctuations. We will see how U is related to curvature fluctuations. It's producing curvature fluctuations out of the tremendous growth of a space-time during the fluid. Again, out of nothing. It's taking energy from vacuum energy that gets converted into fluctuations of the field. So that's the basic physics responsible for the production of particles. Of course, the details are rather complicated, and I think I will stop here since I'm over time, and we will continue tomorrow on this. Any questions? No questions? Have I gone too fast, perhaps? Okay, so let's leave it then for tomorrow. We'll continue from here.